Hey everyone, so this is the Chemistry Regents full review. So this will include everything you need to know for the Regents exam. So before I start the video, I just want to preface a couple things. This video will be divided up into 12 video chapters covering 12 core units. There's going to be around 10-ish practice problems for each unit. Some units have upwards of 15 practice problems, others might have like 8-ish. It all depends. But in total, there's over 150 practice problems, so definitely a lot of practice to do. I would definitely recommend you take out a reference table because a lot of the questions you do need a reference table in order to solve. So also try and do the problems on your own before you watch the solution. That's the only way you're going to improve and actually learn. Now, yeah, that's it, and good luck on your exam, and I hope this video helps you guys. To the question. So base your answers to the following question on the diagram of a molecule of nitrogen shown below. So they just gave us this little diagram here of two circles connected together. Draw a particle diagram that shows at least 6 molecules of nitrogen gas. So for that, we can just draw these molecules together. And you want them relatively far apart and spread out. Let's just pretend those two are connected. It's kind of hard to draw these molecules with my mouse. 1, 2, 3, 4, 5. They won't be in a straight line like this because that's actually scientifically wrong. That you want them all spread out and stuff. But you can also add arrows just to show that they are, just random movement, very erratic. B says draw a particle model that shows at least 6 molecules of liquid nitrogen. So liquid nitrogen, we're going to want them, at least I will draw them in a container, and they will be sort of like together, right? So they're going to be stuck, not stuck together entirely, but very, very close to each other. And this will get a little messy, but it's 5 and 6. Alright, those are some horrible drawings, but I think you get the point. So let's move on to the next question. Base your answers to question 2 through 5. So these ones right here. On the information below and on your knowledge of chemistry, a student prepares 2 141-gram mixtures A and B. Each mixture consists of NH4Cl, sand, H2O at 15 degrees Celsius. Both mixtures are thoroughly stirred and allowed to stand. The mass of each component used to make the mixtures is listed in the data table below. I'm going to start typing my answers because I'm sick of drawing with my mouse. The first question says, describe one property of sand that would enable the student to separate the sand from the other components in mixture B. So when I hear sand, I think filtration, and you have your other components with the H2O and NH4Cl, and they're allowed to stand. So yeah, we can definitely talk about filtration here, and the thing that makes filtration work is their different types of particle size. We can also talk about just solubility if we were to use distillation, but I'll just say particle size. So let me type particle size of the sand varies. Number 3 says determine the temperature at which all of the NH4Cl in mixture A dissolves to form a saturated solution. So for this question, you're going to want to have your reference table, and let's see if I can find the table. So if you go to table G, find NH4Cl, and then we want to dissolve, what is this for mixture A? So mixture A, there's 40 grams of NH4Cl. So we just look on the left side at 40 grams, line it up to the NH4Cl. We can see it's in between 20 and 30 at the temperature. So we can just say it's around 25 degrees Celsius. Which type of mixture is mixture B? So mixture B here has 10 grams of NH4Cl, 31 grams of sand, and 100 grams of water. So it's either homogeneous or heterogeneous. And this one is heterogeneous. I don't think I spelled that right. But it's heterogeneous because it is not the uniform distribution of molecules, right? Because sand has a different density than water, has a different density than NH4Cl, it's not going to be an equal distribution. Versus, let's say we had like salt water, that salt is going to evenly dissolve in that water, and when you draw the particle diagrams, you can see that. Number 5 says, state evidence from the table indicating the proportion of the components in a mixture can vary. So that was basically my explanation before, but we can say that there are different amounts of, in a mixture can vary. Okay, so there are different amounts of NH4Cl and sand in each of the mixtures. So we can see that in mixture A, we have 40 grams of NH4Cl versus mixture B, we had 10 grams. And then since they are the same 141 grams in total, the sand is going to have to vary based on that. All right, let's move on. So base your answers to this paragraph right here. A few pieces of dry ice, CO2, solid, that's kind of important to know it's solid because it's dry ice, at negative 78 degrees Celsius are placed in a flask that contains air at 21 degrees Celsius. The flask is sealed by placing an uninflated balloon over the mouth of the flask. As the balloon inflates, the dry ice disappears, and there is no liquid observed in the flask. All right. Write the name of the process that occurs as dry ice undergoes a phase change in the flask. So we know it starts as a solid. I'll just write this to the side. So it starts from a solid. It says no liquid is observed, and the balloon inflates. So can you guess? It goes from a solid to a gas, because the balloon is inflated by gas. So you're just gonna have to know this. Solid to gas directly is called sublimation. All right, number 7. State the direction of heat flow that occurs between dry ice and the air in the flask. So heat flow, this is another rule you need to know. Heat flows from high to low. So we just look at which one had the higher heat to start with. So the air was at 21 degrees Celsius. CO2, dry ice, was negative 78 degrees Celsius. So the direction of heat flow is from the air to the dry ice. All right, let's move on. Final 3 questions here. So student investigated the heat transfer using a bottle of water. The student placed the bottle in a room at 20.5 degrees Celsius. The student measured the temperature of the water in the bottle at 7 a.m. and again at 3 p.m. The data from the investigation is shown in the table below. So we can see that the mass of the water didn't change, so nothing really evaporated or anything. But the temperature did change. There's a increase of 10 degrees Celsius. Let's see what the question asks here. Show a numerical set for calculating the change in thermal energy of the water in the bottle between 7 a.m. and 3 p.m. All right, so we need to know, let's just write our equation. It doesn't say to, but it's always helpful. So the change in energy is equivalent to mass times the specific heat capacity of our substance, or in this case, water, and then we multiply this by the change in temperature. So we don't need to calculate the actual value, just the numerical calculation. So mass, we know, is 800 grams, because that's just constant in between. And I don't even think you need units here, really. So we can just write this, times the specific heat of water, which is represented by C, that is 4.18. And then the change in temperature, like we said before, is 10 degrees Celsius. Let's see what number 9 is saying. So it says state the direction of heat transfer between the surroundings and the water in the bottle between 7 a.m. and 3 p.m. So the water increased in temperature, and therefore that means the heat must have come from the air. So the heat, heat transfers from air to water. All right. Oh, not from the air. We can just say the surroundings, because maybe it was something else. Oops, I spelled surroundings wrong. Compare the average kinetic energy of the water molecule in the bottle at 7 a.m. to the average kinetic energy of the water molecules in the bottle at 3 p.m. So what is average kinetic energy? That is the exact definition of temperature. So if you have an increased temperature, that means you'll have a increased average kinetic energy. So 3 p.m. equals, why am I still writing? I'm just going to say 3 p.m. has the more average kinetic energy than 7 a.m. The bright line spectra observed in the spectroscope for 3 elements and a mixture of 2 of these elements are represented in the diagram below. The first question says, describe in terms of both electrons and energy state how the light represented by the spectral lines is produced. Well, I'll explain how it's produced. So basically what happens is when you have electrons in, the electrons are neutral and in ground state, they're pretty stable, right? But what happens is they can move up to a more excited state or a higher principal energy level. And when they do that, energy is absorbed. However, they don't stay there for very long because when they're there, they're very unstable. So they end up coming back down. And when they come down from a higher energy level to a lower energy level, that's when energy is released. And that is what produces the light. So the configuration, the variance in the valence electrons and all that is what also determines how these bright line spectras are created. So there we have it. So for number 2, explain why the spectrum produced by a 1 gram sample of element Z would have the same spectral lines at the same wavelengths as the spectrum produced by a 2 gram sample of element Z. Same element, so it have the same, like chemical properties, and the, what is it called, spectral lines, whatever, that is independent of the mass. So it doesn't really matter how much mass you have because the electron configuration for the element is the same thing. All right. Moving on. State evidence from the bright line spectra that indicates element A is not present in the mixture. Well, we can see here, element A, does it line up with the mixture? Well, the first line doesn't. And this one, kind of hard to tell, but it's like slightly off. This one, it does line up with one. This one, kind of hard to tell. But this one here definitely does not line up with the mixture. And so because all the lines match up, we can say that it is not present in the mixture. All right, moving on. Illuminated exit signs are used in public buildings such as schools. If the word exit is green, the sign may contain the radioisotope tritium, hydrogen-3. The tritium is a gas sealed in glass tubes. The emissions from the decay of the tritium gas cause a coating on the inside of the tubes to glow. State in terms of neutrons how an atom of, hydrogen-3 differs from the atom of hydrogen-1. So isotopes, right? So how many protons does hydrogen have? 1, right? It has 1 proton. So all isotopes of a element will have the same protons because protons is what determines what element it is and its properties. So if the only thing that stays the same is the proton number, what has to change? Well, it's neutron number, right? Because if its mass changes, then neutrons plus protons is the mass. And so for hydrogen-3, you have a total mass of 3. And so 3 minus 1 is 2. And for hydrogen, you have a total mass of 1, and you have 1 proton. And so it has 0 neutrons. Alrighty, moving on. A student compares some models of the atom. These models are listed in the table below in order of development from top to bottom. Alrighty. So the first question says, state one way in which the Bohr model agrees with the Thomson model. So the Bohr model is this one right here, and the Thomson model. Let's look at their conclusions. Atoms have small, negatively charged particles. That seems awfully familiar. I mean, yeah, similar to an electron, right? They describe each other. And so the answer here will be that they both describe an electron or small, negatively charged particles. All right, for question 6, it says, using a conclusion from the Rutherford model, identify the charged subatomic particle that is located in the nucleus. So this one is a bit more interesting. So Rutherford model, the observations is most alpha particles pass straight through gold foil, but a few are deflected. So what happens is alpha particles are positive, right? So when you shoot these alpha particles, or at least when he shot these alpha particles through the gold foil, most of them just went straight through, right? So one of his conclusions was that the atom was made of mostly empty space. However, a few were deflected. Now, why? Well, because alpha particles are positive, he concluded that the nucleus was also positive, right? Because like charges repel and opposite charges attract. So if they were the same charge, they would repel, and that's why the alpha particle came back. And we know that what subatomic particle is positive? Boom, protons. All right, number 7. State one conclusion about the internal structure of the atom that resulted from the gold foil experiment. Well, I kind of touched upon that. The atom is mostly empty space. State the model that first included electrons as subatomic particles. So these are in chronological order. So let's just look down at their conclusions. So Dalton model, atoms are hard, indivisible spheres of different sizes. Doesn't really talk about electrons. Thomson model, atoms have, oh yeah, it's this one, because small negatively charged particles, I mean, are you kidding me, man? Yes, it is this one, Thomson model. All right, last 3 questions. The element boron, a trace in Earth's crust, is found in foods produced from plants. Boron has only 2 naturally occurring stable isotopes, boron-10 and boron-11. State in terms of subatomic particles, one difference between the nucleus of a carbon-11 atom and the nucleus of a boron-11 atom. So carbon has 6 protons and boron has 5 neutrons, and they both have a mass of 11, so their neutron number will differ. And we can see here, carbon will have 5 neutrons, carbon-11 will have 5 neutrons, and boron-11 will have 6 neutrons. Number 10, write a isotopic notation of the heavier isotope of the element boron. It has to include atomic number, mass number, and symbol of the isotope. So here's how you would write it. So B, standing for boron, and then on the top number here, you have the mass. So that is the mass number. And on the bottom, you want to write the atomic number. And that just represents the number of protons. Number 11, compare the abundance of the 2 naturally occurring isotopes of boron. So for this question, you'll need your reference table. And if you look at boron, the atomic mass that's stated is 10.81. So if we know that there are only 2 naturally occurring stable isotopes, boron-10 and boron-11, what this means is that boron-11 will have to be more naturally occurring because the atomic mass is the average of all the naturally occurring isotopes. So it's a weighted average, I think. So because of that, the abundance of boron-11 is more naturally occurring than boron-10. All right, so the first question says, identify the noble gas that has atoms with the same electron configuration as the positive ion represented in diagram 1 when both the atoms and the ion are in the ground state. So the positive ion in diagram 1 is this potassium ion. So what happens is we can look at potassium's electron configuration. It's a metal, so it tends to lose electrons. And its electron configuration as an atom is 2881. So what happens is it wants to become stable, right? So if it's 2881, it's going to transfer away one of its electrons to bromine. And then so we're left with 288. So now what we want to do is find a corresponding noble gas that has the same electron configuration as this ion, which is the potassium ion. So if we look on our periodic table, what has the electron configuration of 288? Well, that is going to be argon. So our answer is argon. All right, let's look at question 2. So it says, draw a Lewis electron dot diagram for a molecule of Br2. So bromine and bromine together is just going to have a covalent bond because it's 2 nonmetals, right? And so how I like to approach these questions is add up the total number of valence electrons we're working with. So for bromine, we have 7 valence electrons. So we have two bromine atoms together. So that's 14 total valence electrons we're working with. And so how you would draw it is with this covalent bond in the center, right? So you would draw this bond here. And so we know that this represents 2, right? They're sharing the 2 electrons interchangeably with each other. And so since we know there's 14 in total, we can subtract 2 and we end up getting 12. And so if we do 12 divided by 2, that's 6. And that's an even number. And therefore we know that we can add the 6 to each of the atoms individually. And those electrons don't have to be shared, but it uses all the valence electrons. And so we don't have to add a double bond or a triple bond. We know that we've drawn the Lewis electron dot diagram correctly. So number 3 says, explain in terms of distribution of charge why a molecule of the substance represented in diagram 3 is nonpolar. Well, here's something to note. So you see how it is a symmetrical structure, right? You have carbon in the middle, and then on each of its sides, it has hydrogen. And so that indicates that it is a nonpolar molecule because the distribution of charge is equal. All right, number 4, determine the number of electrons in the bonds between the nitrogen atom and the 3 hydrogen atoms represented in diagram 2. So we can just count, right? So there's 3 hydrogens and 1 nitrogen. And then between each of the nitrogen and hydrogen, there is 2 electrons. So 2 times 3 is 6. And so our answer for number 4 is 6. Number 5, describe in terms of valence electrons how the chemical bonds form in the substance representing, how the chemical bonds form in the substance represented in diagram 1. So how this works is, as we talked about before, because the potassium atom is a metal, right? It wants to become stable and it'll lose an electron in order to do so. Bromine, on the other hand, is a nonmetal, and so it wants to gain electrons because its electron configuration is 2A187, right? So if it gains an electron, it'll become stable. And so what happens is that electron from potassium is transferred over to bromine. So there is our answer. Number 6, explain in terms of element classification why K2O is a ionic compound. So what is an ionic compound? So an ionic compound can consist of a metal and nonmetal. And potassium, we know, is a metal, and oxygen is a nonmetal. So because you have a metal and a nonmetal, that creates an ionic compound. All right, number 7. So there are 6 elements in group 14 on the periodic table. One of these elements has the symbol UUQ, which is a temporary systematic symbol. This element is now known as whatever that is. So it says, state the expected number of valence electrons in an atom of the element of that thing in the ground state. All right, so group 14, we know all the elements in a group have the same number of valence electrons because that's what determines their certain types of properties, right? They're ordered in groups by their valence electrons. And so if you look at group 14 valence electrons, we can see carbon has 4, silicon has 4, and so we can assume that this UUQ also has 4 valence electrons. Number 8, explain in terms of electron shells why each successive element in group 14 has a larger atomic radius as the elements are considered in order of increasing atomic number. All right, so group 14, we can see that carbon has an electron configuration of 2, 4, and then the successive element right below it is silicon with the electron configuration of 2, 8, 4. Right, so it has an additional electron shell, and that increases its atomic radius. All right, number 9. Identify an element in group 14 that is classified as a metalloid. So if you just look at group 14 down the row, you'll just have to notice metalloids are on that staircase thing, right? So one of those metalloids that happens to be in group 14 is silicon. Number 10, explain in terms of electrons why the radius of a potassium atom is larger than the radius of a potassium ion in the ground state. So we kind of talked about this, but we know that potassium wants to lose that electron, right? So originally it's 2, 8, 8, 1. So what determines the radius? The atomic radius is determined by the number of electron shells, right? So its atom has 4 shells, whereas its ion has 3 shells, because after it loses that one electron, that valence electron, to become stable, it has 3 shells. And so, because it has 3 shells, it has a smaller radius compared to its original atom. Number 11 says, explain in terms of atomic structure why group 18 elements on the periodic table rarely form compounds. So compounds are formed in order to either transfer electrons or share electrons in the case of nonmetals, right? Nonmetal and a nonmetal. But we know that group 18 elements are noble gases, and we can just look on the periodic table. Their electron configurations, they all have 8 in their valence electrons. So they've already reached stability, and therefore they rarely form compounds. Number 12, it says, silver-plated utensils were popular before stainless steel became widely used to make eating utensils. Silver tarnishes when it comes in contact with hydrogen sulfide, H2S, which is found in the air and in some foods. However, stainless steel does not tarnish when it comes in contact with hydrogen sulfide. Draw a Lewis dot diagram for the compound that tarnishes silver. So another thing here is just, what are we dealing with? Well, hydrogen is a nonmetal, and sulfur is also a nonmetal. And so we know we're going to have covalent bonds. So I'm just going to actually just draw this out on the side. So we start off with the sulfur, and we have 2 hydrogens, right? So we can just make these covalent bonds, and we have finished the hydrogens, right? Because the hydrogens only need 1 electron, and so they can share interchangeably with the sulfur atom. So how many total electrons do we have? So sulfur has 6 valence electrons, whereas each of the hydrogens has 1, so that's just plus 2. So we have to have a total of 8 valence electrons. Here we know that each of these represent 2, right? So that's 2 times 2, 4. So we still need 4 electrons on this Lewis dot diagram. And it works out nicely because we can just put these 2 on the outside for sulfur. And we know sulfur wants to reach 8, right? So it can reach stability, right? 2, 4, 6, 8. And therefore it is stable. And so that is the Lewis electron dot diagram for H2S. First question says, the volume of 1 mole of hydrogen bromide at STP is 22.4 liters. The gram formula mass of hydrogen bromide is 80.9 grams per mole. What is the density of hydrogen bromide at STP? So this is kind of a weird question, but what we need to do is use the density formula. So the density formula is just density equals mass over volume. And so we can just plug our numbers in. So our mass they give us is 80.9 grams per mole, and we have 1 mole of hydrogen bromide. So that is 80.9 grams over the volume, which they give us as 22.4 liters. So we just do the math there. And I have it under this, so we can see that it is 3.6-ish grams per liter as the density. All right, let's move on to number 2. Identify the type of bonding in solid potassium. So what is potassium? Potassium is a metal, right? So if there's bonding between 2 metals, that indicates that it's a metallic bond. All right, let's go on to number 3. So it says, in 1864, the Solvay process was developed to make soda ash. One step in the process is represented by the balanced equation below. In the space, draw a Lewis dot diagram for the reactant containing nitrogen in the equation. So if we look at our reactants, we can see that over here, the one that has nitrogen as in its equation would be NH3 right here. And so if we were to draw the Lewis dot diagram, we'd have to find the number of total valence electrons. So nitrogen has 5, and then each of the hydrogens has 1. So that's 8 total. So if we draw this out, we have nitrogen, and then our hydrogens on the outside. And we can see that the hydrogens are taken care of, but we have 8 total electrons, and each of these represent 2 electrons. So 2, 4, 6, and then we need 2 on the outside. And so it looks something like that. Let's reveal this, and boom, yeah. I just drew it reverse, but it's the same thing. Write the chemical formula for one compound in the equation that contains both ionic bonds and covalent bonds. So let's look over here. And we have one right here. Let me switch colors. So this one right here, NaHCO3. So let's first identify the ionic compound. So we know Na, sodium, is a metal. So if we combine metal with whatever this is, I see a bunch of nonmetals, that is going to form a ionic compound. And then the covalent compounds is between each of these nonmetals. So CO3 here has covalent bonds. And so that is one of the possible answer choices. Moving on to number 5. Ozone, O3, is produced from oxygen, O2, by electrical discharge during thunderstorms. The unbalanced equation below represents the reaction that forms ozone. Explain in terms of electron configuration why a oxygen molecule, so this is a oxygen molecule, is more stable than just a oxygen atom. So oxygen atom, its electron configuration is 2, 6, so it's unstable. And then for our oxygen molecule, that is where you have something like this. So you have your 2 oxygens. It has 12 total valence electrons it needs to share. So it's like this. We add 2 bonds, because the reason I know to add 2 bonds is because if I have 12 and I have 1 bond, right? That's 2, 10. So I can't share 10 equally in terms of pairs between these 2, right? Because 10 divided by 2 is 5, and I can only have pairs of 2. So if I have 2 instead, so a double bond, I'd have 2 minus, 10 minus 2 is 8. And now this works out because 8 divided by 2 between each of these atoms is 4. And so 4 is an even number I can express in these electrons. So I can just add 2 on each side. Boom. And that gives me a total of 4 pairs. And so we can see here that because this is stable, right, they're sharing electrons in the middle, and therefore they're able to reach stability versus just the oxygen atom, which is 2, 6, which is unstable. All right, number 6. Identify the type of bonding between the atoms in an oxygen molecule. Well, you can see right here, actually, it works out. This thing, covalent bonds, so it is covalent bonding. Boom. And it's also nonpolar because it's the same atom. 7. Draw a Lewis electron dot diagram for a molecule of chlorine. So let's move over here. So we look at chlorine, right? We're going to do the same strategy we did before with these. We look at chlorine. How many total valence electrons? As 7 each. So 7 plus 7 is 14. Let's add our single bond, right? Does that work out? So then I would have 12. So if I do this, then I would have 12. 12 divided by 2, because there's 2 atoms right here, gives me 6. Can 6 be expressed by my valence electrons? Yes, it can. And so I can just add these on the outside. And that should give me 14 total. And therefore, was the question, just draw the diagram, and that should be the diagram right there. So, boom, and there it is. All right, question 8. So explain in terms of molecular polarity why hydrogen chloride is more soluble than hydrogen in water under the same conditions of temperature and pressure. All right, so first let's take a look at hydrogen chloride. So what exactly is hydrogen chloride written out as a chemical formula? So you have hydrogen and then chloride. So I just want to make sure this is balanced. So hydrogen is +1 and chlorine is -1. So this is already balanced. All right. So first off, what type of molecule is it? Well, this is a polar molecule, right? Because there are electronegativity differences indicate that, and it's not the same molecule either. So the distribution of their charges is not equal. So knowing this, why is it more soluble than just hydrogen in water? Well, if we had hydrogen alone, that is not just polar, right? And we know that water, so H2O, is polar. So if these two are polar, and like dissolves like, so polar things dissolve in polar things, and nonpolar things dissolve in nonpolar things. That's why oil doesn't, mix with water very well. Then we know that because they're both polar, and like dissolves like, hydrogen chloride is more soluble in water. Number 9, explain in terms of electronegativity difference why the bond in HCl is more polar than the bond in HI. So for this, take out your reference table and look up their electronegativity. So hydrogen's electronegativity is 2.2, and then chlorine's electronegativity is 3.2. So that's a difference of 1. So let's keep that in mind. So now we want to look at iodine's electronegativity. Iodine's electronegativity is 2.7. So 2.7 minus 2.2 is 0.5. So we know that HCl has a greater electronegativity difference. Now, what does this mean when we're talking about polarity? Well, the greater the electronegativity difference, the more polar it is, because essentially what polarity of a molecule determines within the bond is that the sharing of that charge, right? The sharing of electrons is going to be more unequal for more polar molecules versus a non-polar one. So there we have it. Greater difference means it's more polar. Number 10, the density of hydrogen at STP is 0.0899 grams per liter. Express this density to 2 significant figures. All right, so if we look at this sig figs, right, we're going to start with a decimal. So there's a decimal, so we're going to start on the left side. So if it's 0.0, right? So right now, number of sig figs is 0. But now we have our first term, 8. But we see this is 899. So we can actually round this to just 9. So how many sig figs is this? Well, we just move from the left to the right until we reach the first term. So this is 1 sig fig, so we need another term here. And since we're rounding it, we can just call this 0. Oops. And once we reach the first non-zero number, everything after that counts as a sig fig. So this is 2 sig figs. And so our answer is 0.090 grams per liter as the density to 2 sig figs. All right, number 11, state evidence that indicates NH3 has stronger intermolecular forces than CF4. So if it has stronger intermolecular forces, right? So intermolecular forces, if this is super high, that means it's harder to break apart the bonds and stuff. And so its boiling point should be very high. And its melting point should be very high as well. So we can just look over here. It's the evidence that NH3 has stronger intermolecular forces than CF4. So let's just look at their boiling points and melting points. Is NH3's boiling point higher? Negative 33.3 is indeed higher than negative 427.8. And is the melting point higher? Negative 77.7 is indeed greater than 183.6. And boom, smiley face. Number 12, explain in terms of molecular structure or distribution of charge. So we have an option here. Why a molecule of methane, which is this, NH4, is nonpolar? Well, if we were to draw this out, it would look like this. And we can just talk about the distribution of charge, right? It's a symmetrical distribution of charge, symmetrical molecule here, and therefore it is nonpolar. Equal distribution of charge. Number 13, draw the electron dot diagram structure of calcium chloride. So calcium chloride, let's write this out, calcium, and then chloride. And then once you write this out, you want to make sure it's balanced. So calcium's charge is +2, chlorine's charge is -1, And so if this is +1, +2, and this is -1, we'll need 2 chlorines to balance it out. So now we just need to draw the electron dot structure for this. And something to note here is calcium is a metal and chlorine is a nonmetal. So metal plus nonmetal, ionic bonding. So how you would draw this is like this. So first we want to express the metal. It's a bad bracket. So express the metal, calcium, and then you're just going to draw the brackets and then the +2 on the outside to show that it lost 2 electrons and transfer those 2 electrons to chlorine. So how I like to do is just draw each of the chlorine atoms. So let's just draw the first one. And then the one that gains electrons, so in our case, the 2 chlorine atoms, you will draw in each of those valence electrons. And then outside the brackets, we can just write -1 to show it gained 1, and then do the same thing for this one. There are a couple of ways you can do it as well. You can put like a 2 on the outside of the first chlorine atom to show that there's 2 of those, but that works too. Let's see. Oh, boom. They're drawing electrons when they gain. That was what I was talking about when you would draw in the electrons, the full shell for the atom that gains those electrons. So yeah, that does it for the first one. It says, show a numerical set for calculating the percent composition of mass of silicon and silicon O2. So pretty straightforward. So the equation for percent comp is just, let me pull over here. It is mass of part over mass of whole times 100. So for this question, we can just have the mass of the part, which is the silicon, over the mass of the entire thing of silicon O2 times 100. And so that is the numerical setup. You don't have to write your answer, but you can. You won't get dot points for that, obviously. But yeah, pretty straightforward. So let's move on. Number 2. Determine the total mass of ethanol produced when 270 grams of glucose react completely to form ethanol and 132 grams of carbon dioxide. So this one I'm actually gonna do out over here on the side because it is like more traditionally a mole question. So the first one I like to do is just say what we start off with. So we have what happens when 270 grams of glucose react to completely form ethanol and 132 grams of carbon dioxide. So 270 grams of that glucose. Now I like to put this over 1. All right, because that's our first bracket here. And now we're trying to find the total mass of ethanol. And ethanol is this thing over here on the products. And so in order to get to that, we need to first convert our glucose into moles. So we have 270 grams of glucose, so we want to find how many moles that is. So the gram formula mass for glucose is 180 grams. All right. And then we can just put 1 on top for 1 mole. You'll see the reason I'm doing this is because the grams on both sides cancel. So this is how you know you're on the right track. And so you're left with moles. And so this part of the equation here will tell you how many moles it translates to. But the next thing we want to do is just find the ratio. So we can see that there is 1 mole of glucose, which produces 2 moles of the ethanol, right? So now we just want to convert this. So 1 mole, and then we can just put this over that ratio over 1 mole. So now we're saying that for every glucose mole we produce over here, what we're going to get is 2 moles of the ethanol. And so now we know how many moles of ethanol we have, so we have to convert those moles of ethanol into grams, because that is the total mass. So the gram formula mass of ethanol is 46 grams. We put that on top because 1 mole will cancel with the units. So you'll see here, moles cancel with moles, moles cancel with moles. And now we're left with our final answer of 138 grams. And we can see right here. So yeah, I made sure to spend time on that because that's more traditionally the harder mole concepts of just multi-step layered questions like that. All right, number 3, determine the molarity of this solution. So molarity of the solution, the equation, let me just pull that out. Molarity is moles of solute over liters of solution. All right, so how many moles do we have here? It says in the equation that this 2.5 liter aqueous solution contains 1.25 moles. So we have 1.25 moles on top, and then The second part of the equation is just the liter of solution, and so we just have 2.5 liters on the bottom. So 1.25 divided by 2.5 gives us 0.5 mole. All right, number 4, write the empirical formula for absorbic acid. And it says absorbic acid is also just vitamin C. It has the molecular formula of C6H8. So write this out. C6H8O6. So the empirical formula is just the most condensed, simplified version here. So let's find a common factor between all these. We can divide each of these by 2, right? Simplifying 6 divided by 2. So it gives us 3, and then 8 divided by 2 for the hydrogens gives us 4, and oxygen is the same thing. And so now these don't have a common factor anymore, so that is the most condensed version, which is our empirical formula. Number 5, show a numerical setup for calculating the percent composition of mass of oxygen and absorbic acid. So very similar question to number 1. So we'll just find the total mass of the oxygen, which is 96 grams, over absorbic acid, which is this formula over here. So you can add that up, but I will tell you that it is 176 grams. So that gives you... number 6, determine the number of moles of vitamin C in an orange that contains 0.071 grams of vitamin C. So we have 0.071 grams, and we're trying to find how many moles that is. Well, we know that the gram formula mass is 176 moles per grams per mole, right? So we can just set 0.071 over 176 to find our number of moles. So you'll see here, I did a little differently here, but you can see it's using the same similar setup to number 2. All right, number 7, in the space below, calculate the gram formula mass of glycine. Your response must include both a numerical setup and calculated result. So glycine is this formula up here, that organic compound. So pretty straightforward here. We're just going to literally just add, I'm going to find like nitrogen on the reference table, find its mass, hydrogen, carbon, etc. So it should look something like this, and you should get 75 grams as your final numerical answer. All right, number 8. So we have hydrogen peroxide as a water-soluble compound. The concentration of an aqueous hydrogen peroxide solution, that is 3%. Let's underline that. 3% by mass is used as an antiseptic, and that's the equation for it. Calculate the total mass of H2O2 in 20 grams of an aqueous H2O solution that's used as an antiseptic. It must include both the numerical setup and calculated result. So this is to find the mass here, because they give us the percent composition of by mass, which is 3% they stated. We can just use the same equation we did before with percent composition of mass equals mass of part over mass of whole times 100. So we have the percent composition, which is 3%. And then what we're trying to find is the total mass of H2O2. So that would be our part, because our whole is just the entire solution, which is the aqueous H2O2 solution where the septic has been dissolved in. So we can just call this X, and then 20 grams on the bottom as our whole, and then times 100. And now we just solve for X, and so X ends up being 0. Oops, that's a bad X. So X ends up being 0.6 grams. And we can see here, check. Yes, sir. All right, number 9. Identify the type of chemical reaction represented by the balanced equation. So we have a compound here, right? And it breaks apart into 2 smaller parts. And so that is a clear indicator of decomposition. Boom. All right, number 10. Calculate the percent error of the student's experimental result. Need the correct numerical setup and calculated result. All right, so the student measured... had an accepted value of 20.9%, so that's what he was supposed to get. They did an experiment, and they got it to be 21.4%. So the equation for percent error is just measured minus accepted over accepted times 100. So, like I said before, it's a very heavy on plugging and chugging with equations, but you should get positive 2.39%. Or number 11, determine the total number of moles of oxygen that completely react with 8 moles of C2H6. All right. So if we had 8 moles of C2H6 on this side, in this equation it shows 2 moles, all right? And so we're trying to find the number of moles of oxygen. So for 2 moles, so 2 moles of C2H6, this reacts with 7 moles of O2. So what happens if we bring this up to 8 moles of C2H6? Well, that's a factor of 4, right? So this increases by 4 right here. And so we can pretty safely assume that this will also increase by 4. So what is 7 times 4? That is 28. So we are ending up with 28 moles of O2. And boom. All right, number 12. What is the gram fluid mass of CaCO4? And then that weird symbol 2H2O. So this symbol right here, that little dot, I'm not really sure what to call it, but essentially what you do here when calculating the gram fluid mass is that is the indicator of a plus. So it's sort of like combining these two compounds together, but you can see like the 2 would apply, like you have 2 full H2O molecules, and so what you would do is just calculate CaCO4 together and then add that to 2 times the gram fluid mass of H2O, which I'm pretty sure is 18. So we would get something like this, and our final answer would be 172.2 grams. All right, number 13, given the compound C4H10O8, calculate the molar mass of the compound. All right, so molar mass, pretty straightforward. Just calculate the gram fluid mass of 4 carbons, 10 hydrogens, and 8 oxygens, and then combine them together. And so we should get 186 grams. Calculate the number of moles and 17.7 grams of the compound. So if we have 17.7 grams, we can just set this over, that's ugly 7, put this over 186, right? Because that is the molar mass, which is also the number of grams per mole. And so we should end up getting, boom, 0.095 moles. What is the empirical formula? So what is the most condensed version of C4H10O8? Well, let's see what we can do here. What is the common factor between 4, 10, and 8? Well, that would be 2. So we get C2, H5, H5, and then O4. And since 5 is odd, there's no common factor between these guys. So that is our empirical formula. And the first one says a 2.5 liter aqueous solution contains 1.25 moles of a dissolved sodium chloride, and the equation is below. Compare the freezing point of this solution to the freezing point of a solution that contains 0.75 moles of sodium chloride per 2.5 liters of solution. So it's the same total amount of solution, except the only thing that's changing is the number of moles, and so the concentration has changed. So to sort of illustrate the thinking here, let's say you had 5 grams of water and 1 liter of water. So obviously the more water you have, it's going to be harder to freeze, or at least it's going to take a longer amount of time because there's more surface area, the amount of heat loss changes as well. But if you think about this question, the more concentration you have, it takes away from the existing water, right, in the solution that's trying to freeze. And so what happens is it creates what is called a freezing point depression. So it's going to go down to the extremes. The freezing point is going to be lower the greater concentration you have. So, boom, there we have it. Total of 1.4 moles of sodium nitrate is dissolved in enough water to make 2 liters of an aqueous solution. So it's 1.4 moles of sodium nitrate is dissolved in enough water. The gram fluid mass of sodium nitrate is 85 grams per mole, and it wants us to determine the molarity of the solution. So the molarity equation on the reference table is molarity is equivalent to moles of solute over liters of solution. So how many moles of the solute do we have? Well, we have 1.4 moles right here because it's dissolved in enough water, to make 2 liters of an aqueous solution. So our total liters of solution is 2 liters. And so ultimately this 85 grams per mole, we don't really need that piece of information to solve the problem, but we can just up the equation and we get 0.7 molar. Alright, so number 7. What is the mass of KNO3 that must dissolve in 100 grams of water to form a saturated solution at 50 degrees Celsius? So for this one, go to table G on your reference table, and we know that it has to be dissolved in 100 grams of water, which is nice because the reference table is already in scale with solubility per 100 grams of H2O. And it needs to form a saturated solution at 50 degrees Celsius. All right, so go to 50 degrees Celsius and you're just going to line it up, right? So you can go from 50 degrees Celsius all the way up to KNO3 and then just find where that intersects with the curve of KNO3. And we can see it's in between 80 and 90. So let's say about 84 grams. And so that is the total amount of KNO3 that is going to be dissolved in that 100 grams of water to form a saturated solution at 50 degrees Celsius. All right, number 8. Explain in terms of distribution of particles why the solution is a homogeneous mixture. So what we have here is HCl gas, and it is dissolved in, looks like 200 grams of water at 20 degrees Celsius. And so what happens here is that the HCl becomes H plus ions and is Cl ions. And so these ions are now in that water. And so when you have a gas that dissolves in a liquid like water, it's going to be homogeneous because the particles or those ions will be equally distributed, right? So it's a uniform distribution, and that is what makes it homogeneous. All right, number 9. Based on reference table G, identify in terms of saturation the type of solution made by the scientist. So the scientists made a solution that has 44 grams of hydrogen chloride gas in 200 grams of water at 20 degrees Celsius. So the first thing to notice here is that they give us this in terms of 200 grams of water. So because the reference table is scaled down to 100 grams of water, we need to scale everything else to that proportion. So if we think about this, it can dissolve 44 grams in 200 grams of water, right? So 44 grams in 200 grams of water. So what this means is that, well, the first thing you have to realize is that the more water you have, the more solute that you're going to be able to dissolve. So because of this, if we scale this down to 100 grams of H2O, what do you think will happen to the amount of grams of hydrogen gas that will dissolve? Well, it's going to be halved as well, because from 200 to 100, it's 1/2. So this will go from 44 grams to 22 grams. And so now we can just line this up, right? 22 grams and 20 degrees Celsius, 20 degrees Celsius and 22 grams. We can line it up and we can see that it is under the curve for the HCl line. And HCl is one of those examples that you know it's a gas because the curve goes down. So as you increase temperature, it gets less soluble. So as a matter of fact, even if you didn't scale this down, even if you were at 44 grams at 20 degrees Celsius, you'd still be under that curve. And so it is unsaturated. So let's see here. Boom. All right, so number 10, identify the 2 ions present in the solute. So what is a solute? Looks like it is 3 moles of dissolved NH4Cl. All right, so NH4 and Cl. So pretty simple here. We just want to identify the charges on each of these. So NH4, you can find the charge on table E. NH4 is ammonium, which has a positive charge. So our first one is just NH4 plus, and then our second one will be Cl, and I'm assuming this is a balanced equation, so Cl should be negative. And so that is our 2 ions. All right, determine the molarity of the solution. So very similar to a question we did up there. Molarity is just moles of solute over moles of solution. And so we can just have the moles of solute, which in our case is 3 moles over the liters of solution, which is 2 liters. So 3 over 2 is 1.5. And there we have it. A few pieces of dry ice are at negative 78 degrees Celsius. They're placed in a flask that contains air at 21 degrees Celsius. The flask is sealed with an uninflated balloon. As the balloon inflates, the dry ice disappears and there's no liquid in the flask. Compare the entropy of the CO2 molecules in the dry ice to the entropy of the CO2 molecules in the inflated balloon. So first off, what is entropy? So entropy is just the measure of a disorder of a system, all right? So if we think about it, if we go from CO2 molecules in dry ice, which is a solid, to CO2 molecules in an inflated balloon, where they're going to be gas, right? What happens to the disorder, right? Well, the structure of a solid is much more structurally fixed, right? Versus gas molecules, which go all over the place. And so it's not hard to see which one's more disordered here. It's going to be the gas. And so the entropy of the molecules in dry ice will be less than that of the ones in an inflated balloon. Number 2, describe how the catalyst, zymase, speeds up this reaction. So we've got this reaction here, and it's a pretty simple question that's just asking, what happens if we add a catalyst. So what does a catalyst actually do in a reaction? Well, it doesn't really do anything to the start of your reactants, right? The potential energy of your reactants or your final product, right? You're going to end up with the same thing. So what does it actually do? Well, a catalyst just speeds up your reaction. And so when you have a reaction, let's say we have a chart here. You're going to start off with, let's say, just your potential energy of your reactants. Then it goes through with activation energy, the initial activation energy. And then it's going to drop back down and like this. So this would be like exothermic, or if you had something that was endothermic, it would look like this. Go like this, boom, and then comes back down. And so catalyst at the end of the day is just what dictates this thing right here. All that. So that would be lowered, and so ultimately it would be speeding up the reaction. So it decreases that activation energy. All right, number 3. State the effect on the concentration of the ClO ion when there is a decrease in concentration of the OH minus ion. So OH minus is right here. So it wants us to state what happens to this when this goes down. So let's think about it. If this goes down, because according to Le Chatelier's principle, what needs to happen is this needs to be balanced, right? So if the left side goes down, what happens is the right side has more. And so the right side will start producing and shift this equilibrium position this way to create more and maintain that equilibrium. And so if the products on the right side are being used, that means ClO will decrease. And so ultimately, there's also a decrease for ClO ions. Number 4, explain why the container must be closed to maintain equilibrium. So equilibrium is just the forward and reverse reactions of each of these reactions. And so it needs to be closed. So first off, gas doesn't escape, right? Like Cl2 gas, you wouldn't want that escaping, and that would just mess up the entire reaction. And so also in addition, so like matter doesn't just leave the system. So that is why it has to be at equilibrium. And that's why it has to be closed. So number 5, compare the rate of the forward reaction to the rate of the reverse reaction. So this one, because it's in equilibrium, it's just equal and reversible. Number 8, state 2 methods to increase the rate of reaction and explain in terms of particle behavior how each method increases the reaction rate. So 2 simple ones here are first temperature. All right. So what does temperature do? So if you increase the temperature, you're going to increase the speed of the molecules, right? It's because what happens with that, the particles will then collide with each other much more frequently because they're moving much faster, right? There's an increased likelihood of them colliding with each other. Another one you could use is something like, I don't know, like surface area. So surface area means that there's more area for them to collide with each other versus, so let's add a drawing. Like here, you could hit it at any of these points, right? Any of these points, versus if you had very small, smaller molecules, but increased surface area, you can hit them from all these other angles. And so that would increase the chances for a collision. And so let's see what... You could also increase the concentration, which would mean you would just have more particles in general, which would ultimately lead to having more collisions. So if you have more collisions, that's what ultimately leads to having a greater reaction rate. Number 9, determine the amount of heat released by the production of 1 mole of SO3. So here we have 2 moles of, we have 2 moles of SO3, and this produces 392, it releases 392 kilojoules of energy. So what happens if we only have 1 mole of SO3? Well, this 392 would just be halved to make up for that. And so we get a 196. Number 12, explain in terms of collision theory by using 1 gram of powder zinc instead of 1 gram strip of zinc would have an increased rate of reaction. So if we have powder zinc, that means the surface area is increased, right? Because if we have a strip of zinc, it'll look something like this. So yeah, you could hit it from all these other points. But what happens is that if you have smaller molecules, like powdered zinc, for example, look at all this extra surface area where you can hit it from all these other angles, and therefore increasing the number of reactions, and thus increasing the rate of reaction. Alright, number 13, explain in terms of Le Chatelier's principle why the equilibrium shifts to the right to relieve the stress when the pressure on the system is increased at constant temperature. Okay, so this is something you need to know. What happens when you increase the pressure on the system and you have gases? Alright, so if you increase the pressure, the system will move to the side with less moles. Alright, so that's just something you need to know. And so in our case, if we have 2 moles on this side and 1 mole on this side, if we increase the pressure, it's going to go in the forward reaction, or it's going to go to the right side. So boom, shifts to the side with less moles when the pressure increases. So I'll save you from reading all this. Number 14, the potential energy diagram represents reaction 1. This one right here. You notice there's a lot of stuff. You definitely want to read everything, but sometimes you can get away with not reading the little passage background they give you. So it represents reaction 1 without a catalyst. On the same diagram, draw a dashed line to indicate how potential energy changes when the reaction is catalyzed in the converter. So a catalyst speeds up the reaction, right? And so what happens is, like we talked about before, it decreases that activation energy. And so the potential energy of the reactants is going to be the same thing, except when it comes to this activation energy, it's not going to reach as high. So just go boom. So it's going to follow the same pattern, but when it comes back down, it's going to have the same trend. It's going to finish with the same potential energy of the products here. So curve down somewhat like this. I couldn't really cover that before. First question says, using the data, determine the concentration of HCl, which is the acid. Alright, so the data here is in the passage, so let's actually read that. So a 25 milliliter sample of HCl is neutralized by 15 milliliters of 0.2 molar NaOH, which is our base. So we can just use the titration equation, which is M of the acid. So the molarity of acid, I wanted to write the volume of that acid is equivalent to the molarity of the base and the volume of the base. So we already know the molarity of the base, which is 0.2, and we know the volume of the base, which is 15 milliliters, and we know the volume of the acid, which is 25 milliliters. So then all we have to do is just solve for the concentration, which is just the molarity of the acid. So we accept the equation, and we find that the molarity is 0.12 mole. Based on the data, the calculated molarity of HCl should be expressed to what number of significant digits, or figures. So for multiplication, how sig figs work is you're going to find the number of sig figs in each of the values that you calculate, and then you have to round to the one that is the least number of sig figs. So in our case, we have 25.0, which has 3 sig figs. And then we have 15.0, which also has 3 sig figs. And then we have 0.20, which has 2 sig figs, right? Because when you're counting with a decimal from left to right, you don't negate the 0. And then once you reach 2, that's just 1 and then 2 sig figs. So we have to round to 2 sig figs here. And so that is our answer for 2. Number 3, complete the equation for the neutralization reaction that occurs by writing a formula for each product. So what is the neutralization reaction? So a neutralization reaction is where an acid and a base come together to create water and a salt. And so water, we know, is just H2O, right? So the easy way to solve these problems is to just take out H2O. So we have the H from the HCl, and then the other H and the oxygen from the NaOH. So we can just cross this out and make our first product, which is H2O. And so now we just need to determine what the salt is, and we just have the remaining product. So we have Na and Cl, so we just combine those two, and they're already balanced, by the way. So we just create NaCl as our salt, and that is our answer. Number 4, to identify the laboratory process described in this passage. So this passage, basically. Well, we kind of talked about this. We used the titration equation and talked about a neutralization reaction. So can you guess? Yep, titration. All right, number 5, say how many times greater the hydronium ion concentration in HCl is than the hydronium ion concentration in whatever that is. So we're comparing a pH of 2 to a pH of 3. And we know that hydronium ions increase as you become more acidic, right? And we know that a pH of 2 is more acidic than a pH of 3 by a factor of 10 because it scales, right? So if we had a difference between 2 and 4 in terms of pH, that would be a difference of 100. But in our case, the difference between 2 and 3 is just 10. And so the hydronium ion concentration also has a factor difference of 10. Number 6, complete the table by writing the color of thymol blue in the NaCl aqueous solution and in the NaOH aqueous solution. So for this one, just go to your reference table, and let's see if I can find it. Go to table M, and we're just going to compare the pH and what they would be in terms of the color change. So for NaCl, we have a pH of 7, and then the color in thymol blue. Thymol blue ranges from 8 to 9.6, which gives you yellow and blue respectively. And so because the pH of 7 is under 8, we're going to have a color change of yellow for NaCl. Boom. And then for NaOH, we have a pH of 12. 12 is above 9.6, so we're going to get blue. All right, let's move on. So number 7, determine the concentration of KOH. And this is another titration question. So we can just set up our equation with molarity of the acid times the volume of the acid equals molarity of the base times volume of the base. So here we're just trying to find the molarity of our base here. So we just set up the equation like so. We find the molarity is 0.17 mole. Number 8, compare the number of moles of H plus aqueous ions to the number of moles of OH minus ions in the titration mixture when the HCl aqueous is exactly neutralized by KOH. So if it's neutralized, so the first thing I think would be useful here is what exactly is titration? So titration is where, like, let's say you have, this is not a really accurate drawing, but let's say you have like a beaker here, and you have, I don't know, like a base. I don't know what base this is. Let's just call this, let's call this KOH, because that's the example they gave us. So let's say you had KOH in here, and then it's like mixed in weird solution. And then up here you had your acid, right? So you had HCl. So what you would do is you would incrementally, so you add like drops of this HCl, right? You would add drops of this into the KOH until it turns color. So you have some sort of indicator in there that shows you when it turns slightly acidic. And so when it just turns slightly acidic, remember it starts as a base, then the difference in between how much HCl you use or how much acid you use will tell you a lot about either the molarity of the solutions, or in our case, the number of moles. And so if it just turns acidic, you're trying to get it to not turn acidic, to be honest. You're just trying to neutralize it, or you're trying to strike a balance at a pH of 7. So if you strike a balance at a pH of 7, that is where you have a balance, actually, of H plus ions and OH minus ions. And so in our case, it would be, oops, I keep clicking the equals sign, but they would be equal. I feel like this titration thing right here, this was kind of irrelevant for this question, but whatever. Number 9, carbonated beverages are made by forcing carbon dioxide into a beverage solution. When a bottle of one kind of carbonated beverage is first opened, it has a pH of 3. So when it's left open for several hours, hydronium concentration decreases to 1/1000th of the original concentration, determine the new pH of the beverage. So the hydronium ion, we talked about this before, hydronium ions stick with acidic solutions, right? And so if it decreases, so if this hydronium ion decreases, we know it gets more basic. So the pH will increase. And it starts at a pH of 3, right? And since we know that each pH that goes up is a factor of 10, and we have 1/1000th, so if we go to 4, 5, and then 6, so from 3 to 4, it'd be 1/10th. Hydronium ion concentration, 4 to 5 would be 1/100th, and 5 to 6 is just 1/1000th. Actually, this is inaccurate. It's 3 to 4 is 1/10th, 3 to 5 is 1/100th, and 3 to 6 is 1/1000th. So in our case, the new pH would be 6. All right, number 10. State in terms of the pH scale why this beverage is classified as acidic. Well, it's under 7. 7 is neutral. Anything under it is acidic. Anything above it is basic. So, yeah, pH under 7. Number 11. Identify the negative ion found in milk of magnesia. So, milk of magnesia, it's a mixture of magnesium hydroxide, which is I should actually read this. So in liquid water, a equilibrium exists between H2O molecules, H plus ions, OH ions, okay? And if someone is experiencing acid indigestion after drinking tomato juice, they can ingest milk of magnesia to reduce acidity. So I'm assuming it's basic, okay? So tomato juice has a pH of 4, milk of magnesia has a pH value of 10. Okay, that makes more sense. Okay, so because it has a pH value of 10, it's above 7, right? So 7 is neutral, so 10 is basic. So negative ion there is just going to be the ion that's associated with bases, which is OH minus, because we know that hydronium or H plus ions are associated with acidic solutions. So in our case, it would be OH minus. All right, number 12. Compare the hydrogen ion concentration in tomato juice to the hydrogen ion concentration in milk of magnesia. So tomato juice is obviously more acidic. So because we're talking about hydrogen ion concentration, hydrogen ions are more concentrated in acids than bases. So boom, tomato juice has a greater hydrogen ion concentration. It says compare the intermolecular forces of the two substances at STP. So the two substances here is ethane, which has a boiling point of negative 89 degrees Celsius at STP, and then ethanol, which they say has a much higher boiling point than ethane at STP. So intermolecular forces are just the bonds in between molecules in these substances. And so if you have a much higher boiling point, what that means is it's going to take a lot more energy to break those bonds, right? So if it takes more energy to break those bonds, it means the bonds are stronger, and so the intermolecular forces of ethanol are stronger. There you go. All right, number 2, a liquid boils when the vapor pressure of the liquid equals the atmospheric pressure on the surface of the liquid. Based on table H, what is the boiling point of ethanol at STP? So for this question, we can just take out table H, and then we're going to go down to STP and see where it lines up. So we can see on the dotted line where it says 101.3 kPa, that line intersects at a point with ethanol, right? So then we can go down here and see what temperature that lines up with, and we can see it's around 80 degrees Celsius. So our answer is 80 degrees Celsius. Number 3, show a numerical setup for calculating the volume of the gas in cylinder B at STP. All right, so it looks like we have cylinder A is a movable piston and has hydrogen gas, and cylinder B is the exact same thing except it has methane gas. And then it looks like between the two gases, the pressure is the same, the volume is the same, and the temperatures are also the same. So if we want to find, if we're just looking at cylinder B, right? So these conditions, the pressure conditions right here and the temperature conditions are currently not at STP. So for STP, the temperature is 173 Kelvin, and then the pressure is just 1 atmosphere. All right. So in order to solve for the volume, because right now we don't know what the volume is at STP, we will have to use the gas laws equation. And the gas laws equation is just pressure of 1, volume of 1, over temperature of 1. So these are just the initial conditions. So we know all 3 of these variables. And then we're just going to set this equal to the pressure of 2. In our case is 1 atmosphere over the temperature of 2. We know it would be 273 Kelvin for STP conditions. And then we're just going to solve for the final volume here. And so if you plug in the numbers, you should get that. So we only need a numerical setup. We don't actually have to solve for V. Number 4, state a change in temperature and a change in pressure that will cause the gas in cylinder A to behave more like ideal gas. So you're just going to have to know this off the top of your head. So ideal gases, they want to have high temperature and lower pressure. Now real gases, in contrast, have lower temperature, are closer together, and therefore have high pressure. But ideal gases, you want high temperature and low pressure. Number 5, compare the total number of gas molecules in cylinder A to the total number of gas molecules in cylinder B. So this is gonna have to, you're gonna really have to read in between the lines here. So if we look at the volumes here, we have 1.25 liters of gas here and 1.25 liters of gas here. And since pressure and temperature are constant between the hydrogen gas and the methane gas, because the volume is the same, you're also going to have the same number of gas molecules, right? So the amount of gas molecules is going to be constant between the two as well. So it is the same. All right, number 6. Compare the total number of gas particles in the sample under the initial conditions to the total number of gas particles in the sample under the final conditions. So let's read up here. It says a sample of helium gas is in a closed system with a movable piston. Volume of the gas is changed. Okay, so basically you have a closed system and has a movable piston, and there's some, just gas particles in here. And what they did is they increased both the temperature, right? Temperature went from 200 Kelvin to 300 Kelvin, and they also increased the pressure from 2 atmospheric to 7 atmosphere. So we don't know what happened to the volume, but right now the first question here is asking about the total number of gas particles. So because this is a closed system, it doesn't really matter what we do to the temperature or the pressure. The total number of particles, because it's a closed system, no matter can escape. And so the total number of gas particles will be the same as well. Number 7, convert the final temperature of the helium gas sample to degrees Celsius. So pretty straightforward. This equation is in your reference table. So Kelvin is equivalent to Celsius plus 273. And so in our case, we know the Kelvin, so we want the final temperature into degrees. So the final temperature is 300, right? So we just write 300. And it's just some simple algebra. We can just subtract 273 to find our Celsius. So that should be 27. Boom. Number 8. In the space below, show a correct numerical setup for calculating the final volume of the helium gas sample. So this question right here uses the gas laws again. So it's the same equation that we talked about up here. And I'm pretty sure it's the same missing variable too. Let me just check. Yeah, because we're trying to find the volume of this one as well. So for this one, we would just plug in. So for P1, that would just be 2. For V1 right here, that would just be 500. And then for the initial temperature, just 200. Final temperature would be 300. And then final pressure would be 7. And then we can just solve for the final volume. And so you should get that. All right, number 9. When the airbag inflates, the nitrogen gas is at a pressure of 1.3 atmospheres, a temperature of 301 Kelvin, and has a volume of 40 liters. Calculate the volume of the nitrogen gas at STP. Your response must include both a correct numerical setup and calculated volume. So this question is another gas laws question. All right, so let's just set this up this time. So we know that it starts with a pressure of 1.3 atmospheres, has a temperature of 301 Kelvin, and 40 liters. So let's make this out like this. Boom. And then it's going to calculate the volume of nitrogen at STP. So STP conditions, you have to pretty much know this. It's on the reference table, by the way. So STP conditions, 273 Kelvin, 1 atmosphere, and then we're just solving for that final volume. So that final volume I've calculated right here, but you need both a correct numerical setup, which is this thing over here, and also the calculated volume. So I don't put units, but you probably should put units in the actual regions. But yeah, there we go, 47.2 liters. All right, number 10, balance the equation for the decomposition of NaN3 using the smallest whole number coefficient. So for this one, here's what I'd like to do. So let's write this out. NaN3 goes to Na, reduce process, boom, boom, boom. All right, so here we have a voltaic cell which has zinc on the left side, the anode, and then it has iron on the right side as the cathode. And it says the cell and the unbalanced ionic equation represent the reaction that occurs in the cell are as follows, shown below. Number 1 says explain in terms of zinc atoms and zinc ions why the mass of the zinc electrode decreases as the cell operates. So this is the electrode right here. So what happens is, because this is the anode, zinc is going to be losing electrons, right? So part of this is going to just like fly off as electrons come off, and so the mass actually decreases. And you can see this in the equation, right? You have zinc solid going to zinc plus 2. Now this plus 2 means that it's lost 2 electrons. And so the mass of the zinc electrode decreases as it operates because it is oxidized. All right, number 2, identify the subatomic particle that flows through the wire as the cell operates. So this is the wire right here that connects the anode and cathode. So what flows through here are the electrons. Now the salt bridge thing, that's where the actual ions will flow, and that just keeps it balanced between the 2 electrodes. But for number 2, that is going to be electrons. All right, moving on. Number 3, write a balanced half reaction equation for the reduction of the iron ions and iron 3 oxide to iron atoms. All right, so for this one, we're going to start off with our iron 3, iron plus 3, because it wants us to show the reduction for iron 3 oxide to iron atoms. So we're going to have an addition of 3 electrons, and that is all going to go to iron, 1 iron atom. So the reason for this is because in these redox reactions, there's going to be a conservation of mass and conservation of charge, right? So the charge on this side, plus 3, on this side is going to be 0. And so we have that -3 from those 3 electrons, and so this cancels out and gives us 0. And then we have 1 mole of Fe, 1 mole of Fe, and then electrons mass is negligible. So, and there we have it. So number 3, boom. All right, number 4, identify one metal from the passage that is more active than carbon, and one metal from the passage that is less active than carbon. So, in this passage here, it says metallic elements are obtained from their ores by reduction. Some metals such as zinc, lead, iron, and copper can be obtained by heating their oxides with carbon. So we can pick from any of these. We can pick zinc, lead, iron, copper, doesn't matter. All right, so for this one, we can just pick something like zinc. And now for the one that is more active, we can just look below. It says more active metals such as aluminum, magnesium, and sodium cannot be reduced. So let's just pick aluminum here. So yeah, there we have it. Identify the component required for electrolysis of molten NaCl that is missing from the cell diagram. So basically, this is electrolysis, and it can't really operate right now because it's missing something in the middle. And what is that something? Well, it is energy. Right? It needs a power source. And so the answer for this is a battery. All right, number 6, state in terms of energy why the cell is a voltaic cell. All right, so it's a voltaic cell because, first off, is there a battery? No. So there is no battery. And so what we want to look for is how energy is created, right? So these electrodes, the redox reactions that they go through, the half reactions that they go through are producing chemical energy. Chemical energy. And this chemical energy ultimately is going to power this entire system, right? So it's like a circuit of electrons that flow through. And so this chemical energy will go and create electrical energy. And so in this case, because it goes from chemical energy to electrical energy, that's how you know it is a voltaic cell as opposed to something like electrolysis, which requires a battery. So there we go. Number 7, determine the number of moles of aluminum needed to completely react with 9 moles of nickel ions. So we have 2 aluminum, which reacts with 2 moles of aluminum reacts with 3 moles of nitrogen. All right. Oops. So if we have a ratio of, so we have 9 moles of nickel, and so if initially we had 3 moles of nickel, and this gave us 2 moles of aluminum, that is a 3 or 1.5 ratio, right? And so we can do the same thing here. It's just 9 divided by 1.5 equals, and that should give us, boom, 6. All right, number 8, write a balanced half reaction for the oxidation that occurs when the switch is closed. All right, so oxidation means a loss of electrons. So let's see which of these electrodes actually loses electrons. So we can see here the aluminum goes from a neutral charge of 0, and it goes to, looks like +3. And so it is actually losing 3 electrons. And so we know that aluminum, the solid aluminum in the electrode, is being oxidized. And therefore, if we were to write this out, let me do this to the side, we would start off with our 2 aluminum, right? And this is already balanced. And so this would just go to, it's losing electrons. So the electrons would be on the right side. And then our products is right here. So 2 aluminum, and it's +3 ion. And then we have to add our electrons, right? So if this is 6, this is a +6, we need a -6. And so we need 6 electrons. So that is one of the answers for 8. You could also simplify this. So you could say like just 1 mole of aluminum solid is equivalent to 1 mole of aluminum ion plus 3 electrons. But either one works. Number 9, state the direction of electron flow through the wire when the switch is closed. So electron flow flows from the anode to the cathode. So in our case, the anode is just the aluminum, and that's where electrons are lost. And so the electrons will just go like this. So left to right. So boom. All right, number 10, explain in terms of Ag atoms and Ag ions why the mass of the silver electrode decreases as the cell operates. Well, pretty similar situation here, except we have a power source, right? So this is a electronic cell right here. So Ag is our anode, all right? So that's going to be oxidized. So when we oxidize it, it's going to lose electrons. And like we talked about before, if you lose electrons, you're going to be losing mass as well. So, boom. Number 11, state the purpose of the power source in the cell. Well, the power source is really what drives this reaction. So the purpose of this power source, or in our case, I'm assuming it's a battery here, is to drive the spontaneous reaction. So, boom. All right, number 12, identify the cathode in the cell. Well, we kind of did that because we said it starts in the anode with the argon, and then we end on the other side, which in our case would just be nickel, right? So our nickel solid is going to be the cathode. So the nickel key. All right. So the first question says, draw a structural formula for the hydrocarbon that is approximately 2% of natural gas. And so we want to read this thing up here. And it says that natural gas and coal are two fuels burned to produce energy. Natural gas consists of approximately 80% methane, 10% ethane, 4% propane, and 2% butane. So that is the 2% natural gas. And that butane is a hydrocarbon that we're trying to draw. All right, so let's go on the side here. So how do we draw butane? Well, first let's identify that prefix, right? And the prefix is but. And so but, this prefix here, tells us a lot. So it tells us the number of carbons that are in this hydrocarbon. So if you go on your reference table and you go to table P, it says that the but prefix means that there are 4 carbons. So we know that for our structural formula, we're going to have 4 carbons. And now let's look at the ending, right? So it's butane. So it is part of the alkane homologous series. And so what this means is that there are single bonds. So single bonds. And now why is this important? Because if we know that there are single bonds, that helps us determine how many hydrogens we have, right? So first, if we were to draw this, let's just write out our 4 carbons. And then we'll connect them. We know there's single bonds because it's the alkane series. And now we want to figure out how many hydrogens there are. Well, we can use the formula that is provided on the reference table as well. If we go to table Q, alkanes, the general formula is as follows. So carbon, N, hydrogen, 2N plus 2. So what does this mean? So N is just the number of carbon atoms, right? So in our case, we would have C4 because we have 4 carbons. And then we just plug in 4 for N here. So we have 2 times 4 is 8 plus 2 is 10. So you have 10 hydrogens. Now it works out because if we just draw a hydrogen on each of these remaining parts on the carbon, we can see that we will have 10 hydrogens. So that is the structural formula. Number 2, write the general formula for the homologous series that includes the components of the natural gas listed in this passage. Well, we already did that right here. That is the general formula you can use to help you determine how to draw your structural formulas. And for questions like these, very helpful. So there we have it. All right, number 3, identify the class of organic compounds to which ethanol belongs. So ethanol, it says up here that ethanol is C2H5OH. So how exactly do we determine what class this compound is in? Well, we want to look for that functional group. So this functional group here, we can see we just have the regular carbon, hydrogen, but now we have this OH right here. So this OH tells us a lot because that is the functional group, OH, the functional group for alcohol, right? So that indicates that ethanol is a part of the alcohol class. Now, another way you could look at this is just by the ending, right? So we have ethanol. So we have that, let's bring this over. We have that anol ending. So where else can you find this anol ending? Well, if you look at the reference table, table R, we can see that the example for alcohol is 1-propanol. So we can see that same ending here, and so you can use that comparison. Let's use a highlighter. You can use that comparison, and that's actually bad. But you can see the anol, so that lines up, and so we know that it is a part of the alcohol class. All right, number 4, to which class of organic compounds does ethyl stearate belong? So where is ethyl stearate? So ethyl stearate is this thing right here. And so we're just going to look at this structural formula and figure out what class it belongs to. So we have a single bonded oxygen on this side and then a double bonded oxygen on this side. So let's look on our reference table R. The reference table is your best friend. And we can see here that it lines up nicely with the ester. All right, so we have an ester. The functional group has a double bonded oxygen and then a single bonded oxygen as well. So it lines up there, and therefore we can determine that this ethyl stearate is a part of the ester group. 2 hydrocarbons that are isomers of each other are represented by the structural formulas and molecular formulas below. Explain in terms of structural formula and molecular formula why these hydrocarbons are isomers of each other. So isomers, all right, you're going to have to know this. Pretty straightforward though. So isomers essentially have the same, actually it's faster if I just type this out, to be honest. They're going to have the same molecular formula, but they're going to have different structural formulas. All right. So what this means is, if we take a look case at hydrocarbon 1 and hydrocarbon 2, we can see that for the first one, they both have a molecular formula of C5H8, right? So if you count up the total carbons and hydrogens, they line up. However, if you were to count the actual naming of these hydrocarbons, right? So that would be determined by the structural formula. That would be different, right? Because here we have double bonds, and here we have triple bonds, and the bonds are also in different locations. So in our case, we can just say it has the same molecular formula in different structural formula. All right, number 7, write the name of the homologous series to which the hydrogen belongs to. So in this case, we have looks like a reaction between bromine and a hydrocarbon. So this is the bromine, and so this is the hydrocarbon in question. So we can see here immediately we have a double bond, and that indicates, table Q, double bonds are a part of the alkenes series. So the answer here is alkenes. Number 8, identify the type of organic reaction. So what's happening here? Let's erase this. So we can see very clearly there is a addition symbol. So here we can just very confidently just say this is addition. So what happens here is you'll see that double bond that was existing before in this hydrocarbon is broken down in order to make room for these bromine atoms to add on to the existing hydrocarbon. So there we can say addition. All right, number 9, explain in terms of bonding why C3H6 is classified as an unsaturated hydrocarbon. So unsaturated hydrocarbons are going to have either double bonds or triple bonds, because saturated hydrocarbons have single bonds. And so is C3H6 a part of the alkane series? Well, it's not, because the alkane series, like we talked about before, it follows this formula here. So in our case, we have 3 carbons and 6 hydrogens. It does not follow the formula here, because here, if we had 3 carbons, we would have 8 hydrogens. Instead, this follows the formula for alkenes. Yeah. So this follows the formula for alkenes, and therefore it's going to have a double bond, and so it is a unsaturated hydrocarbon. All right, the last question here, number 11. In the space below, draw a structural formula for a molecule of 2,2,4-trimethylpentane. So when you get these types of questions, how should you approach them? Well, first, I would identify on the very right side what you actually have as the base of the hydrocarbon. In our case, that is pentane. So this is not one of those fancy alcohol, ester, ketone, whatever. So we can just draw out pentane, right? So we have pentane. So pentane, the prefix pent, the reference table P has 5 carbons. So we can just draw 5 carbons. And these are single bonds as well because the prefix, the suffix at the end is ane. Ane, the alkanes group, has all single bonds. All right, so now let's approach the next part, which is the trimethyl. So trimethyl means there's going to be 3 additional methyls that are attached on each of these carbons. Now, where are these going to be attached, right? Like, which carbons are these methyls going to be coming off of? And this is where this part comes in. I wish I could switch color, but whatever. So 2, 2, 4. What does this mean? That means you're going to have methyls on both sides of the second carbon, and then 1 on the 4th carbon. So I'll show you what I mean right here. So if we were to draw this out, we would have 2, 2. So this would be the second one. So the first carbon right here. And so this would be the second carbon. So then we could just draw a CH3, which represents methyl, like this. Let's erase this at the bottom. And we can have another CH3. So in reality, these aren't really 2D. They're 3D and can move around and all that. But that's just how you want to draw it in this case. Now for the 4s, we just count here. So this is 1, 2, 3, 4. So we know our 4th carbon is right here. And let's attach another methyl. So now we finished the trimethyl. So tri means 3. We have 3 methyls there. And now we just have to complete the rest of the molecule. So carbon here, we can just add a hydrogen to each side of this. Same thing here. And same thing here. Boom, boom, boom. Nothing fancy here because if we zoom in on this right here, it's a single bond between those 2 carbons. So it looks like this. Oops. It's going to look like this. Boom, boom, and then boom, boom, boom. So it says a breeder reactor is one type of nuclear reactor. In a breeder reactor, uranium-238 is transformed in a series of nuclear reactions into plutonium-239. The plutonium-239 can undergo fission as shown in the equation below. The X represents a missing product in the equation. All right, so the first question wants us to write a notation for the nuclide represented by the missing product X in this equation. All right, so for all these fission reactions, there's going to be a balance of charge and mass. All right, so here we can see on the left side, we have a total mass of 240 and then a total charge of 94. And on the right side, we have so far 94 plus 1. So we have a mass of 95 right now, but ultimately we need to balance the mass, so it's 240 on the left side. Oops. So if it's 240 on the left side, we want to subtract 95, and that gets us 144. So our mass is going to be 144. So for our final answer, we can write like 1. Oops, this is not good at all. Let's write 144 over here. All right, now for the bottom side, we have 36 on the right side and 94 on the left side. So that is a difference of 58. So we can write 58 on the bottom. So this 58 right here also represents the protons, all right? So because we know the number of protons, even though this may be an isotope of an element, then we can determine what that element is. In our case, that is going to be Ce. So there we go. And so that should be the nuclide, the missing product X in this equation. There we go. All right, number 2, compare the amount of energy released by 1 mole of completely fissioned plutonium-239 to the amount of energy released by the complete combustion of 1 mole of methane. All right, so here's the thing, right? So combustion is a chemical reaction or a chemical process, whereas fission is nuclear. And the thing is, nuclear reactions and processes release a lot more energy than chemical ones do, right? So like nuclear, think like atomic bombs, right? Just a vast amount of energy, very unstable. And so in our case, it would be the fission of plutonium. So fission does release greater amounts of energy. Number 3, based on table N, identify the decay mode of plutonium radioisotope produced in the breeder reactor. So pretty straightforward, just go to your reference table on reference table N. So you won't find plutonium there, but you want to like read the question, right? So it says it goes from uranium-238 to plutonium-239. So what you want to do is just look for the decay mode of uranium-238, which in this case is alpha. So there we go. That's the alpha symbol. All right, number 4, determine the number of neutrons in an atom of the uranium isotope used in the breeder reactor. All right, so if we write out uranium, and I should just use another color for this, uranium, it's 238 for its mass, and then it has 92 protons, or 92 protons. Well, pretty straightforward. We just find the difference between mass and the protons, and we get the number of neutrons, which is 146. And so there we go. Boom. All right, number 5. Complete the nuclear equation for the radioactive decay of tritium by writing a notation for the missing part. So tritium is also known as hydrogen 3. All right, so hydrogen 3, good to know. They were listed right here. So balance of mass and charge. So on the on the left side we have a mass of 3. On the right side it's 0 because the electron is negligible in mass, and so we know we have to write a 3 on the top. All right. On the bottom we have a 1 on the left side and a -1 on the right side, and so to balance that out we need a 2. And so what has 2 protons? Well, that's going to be helium. So that is going to be that notation for that part. Boom. Number 6, determine the fraction of a original sample of tritium that remains unchanged after 24.62 years. So this is a half-life question, right? So first off, what is the half-life of tritium, or hydrogen 3? Well, on the reference table, it states that the half-life is 12.31 years. So that's just something to keep in mind here. Now, it says the fraction after 24.62 years. So this is the total amount of time that has elapsed, and this is the total half-life. And so each half-life, 50% of it decays. And so we have 24.62. And how many times does 12.31 go into 24.62? 2 times. So that is 2 half-lives. That is very messy, but whatever. So 2 half-lives pass. All right, so let's write this out. It wants the total fraction. So we start off as 1 because that's just 1 whole. And then after 1 half-life, it decays to 1/2, right? And then it decays 1/2 again. So what's 1/2 of 1/2? Well, 1/4. And so that is our fraction. And I did another way here, but both ways work. All right, moving on. Number 7. Determine the total amount of time that has elapsed when 12.5 grams of the original cobalt-60 sample at the hospital remains unchanged. So what is the original sample here? So it says the hospital keeps a 100-gram sample of cobalt-60. Okay, cool. So we start off with 100, right? And it wants us to know the total amount of time that it will elapse when it reaches 12.5 grams. Okay, so 100 will decay to 1/2 of 100 is 50, so that's 1 half-life, and then it decays to 25, that's 2 half-lives, and then it finally decays to 12.5. So how many half-lives is that? Let's count. So this is 1, 2, 3 half-lives. Okay, so you have 3 half-lives, right? So what is the actual half-life, like the time that it takes to go through 1 half-life for cobalt-60? Well, you can go on your reference table, and the reference table says, let's pull this out, let's see, it says 5.271. All right, so 5.271. I'm not sure what that is, but whatever that is together should be the total amount of time that has elapsed. So 15.8-ish years. All right, number 8. Complete the nuclear reaction below for the beta decay of cobalt-60 by writing an isotopic notation for the missing product. All right, so very similar question like the ones we've done before. Left side is 60, right side is 0, so we need 60 on top. Okay. Left side is 27, right side is -1, so we need 28. So what has 28 protons? Let's check. Looks like nickel. All right, so nickel has 28 protons, and so that should be our notation for that question. Number 9, compare the penetrating power of the two emissions from cobalt-60. Alright, so if we look above here, I wonder if the highlighter actually works. It says that the cobalt-60 is the artificially produced radioisotope that emits gamma rays and beta particles. Okay, wow, that actually looks very realistic on the paper, but whatever. But yeah, so it emits gamma rays and beta particles. So gamma rays have no charge, right? So when you put it through a magnetic field, it's just going to go past. Whereas beta particles are negatively charged, and so they will actually get deflected. And so here, gamma rays have a much stronger emission penetrating power. So yeah, there we go. Number 10, state one risk to human tissue associated with the use of radio isotopes to treat cancer. Well, here's the thing. It's radioactive material, right? So, I mean, if you get it inside your body, okay, it can kill the cancer cells, but it also poses a big risk to the healthy cells. So, yeah, boom, there we go. It can be harmful to healthy cells. So that does it for the review of Unit 12, and that concludes chemistry, Regents at least. So yeah, hope you guys learned something. If you did, make sure you subscribe, and thank you for watching.